On something other than organic chemistry. Outstanding. This will be a fun class. All right, guys, let's go ahead and get started. All right, we're going to pick up where we left off the other day. I think, if I remember correctly, the last thing we did was syn dihydroxylation. Is that right? Okay. So, you know, again, like with, you know, a couple of the other oxidation techniques, I'm not really concerned about you guys learning the mechanism. It's honestly more trouble than it's worth here. But being able to remember the fact that using strong metal oxidizer like the ones we listed with an alkene will give you those two OHs on the same side. I'm not going to go over the mechanism, but I am going to give you a brief sort of indication on why this proceeds via a syn addition and not via an anti-addition, right? So if you have an alkane, it's going to be an alkene, right? We said we needed a strong metal oxidizer. One of the ones we mentioned as an example was potassium permanganate, right? And I drew the structure of the permanganate ion the other day. Draw it again. Okay, it looks like that. Right? Now, whenever you add to the double bond, well, what gets added to the double bond? How many oxygens? Seriously, not a trick question. I'm trying to get you guys just, you know, interact. Battle of Wills, I'm going to just stare at you until you say something. Two, thank you. It's like, dear God, just move on. Yes, two, right? All right, well, when we added two oxygens previously in the anti-dihydroxylation, we saw one of them came from the epoxidation step, and one of them came from the other step, the second step that we use. This one's a little bit different because this is not a two-step process. Guess where both of the oxygens have to come from in this case? Where do they come from?
That molecule.
That ion, yes. The permanganate. So by nature, this whole thing kind of flutters in, right? And two of these four oxygens have to come from the same spot or the same source to oxygenate those carbons, right? So because they're literally attached to the same atom, they have to be coming in from the same side. That's why you always get a syn dihydroxylation whenever you do this. Whenever you do anti, if you think about it, you have to make an epoxide first. The second step is breaking open the epoxide, and how do we learn that always occurs? By anti-addition, right? So that's why one of them can give you syn, the other one can give you anti. Excuse me. Does that make sense? Are there any questions about that? All right. All right, a couple more. All right, the next thing we're going to talk about is going to be oxidative cleavage. And the name here is pretty descriptive, right? When you cleave something, what are you doing to it? You're breaking it apart, right? You're dividing it into more species, right? So that's what we do here. We're going to take an oxidative cleavage. We're going to take a molecule and we're going to break it up into smaller pieces. And those pieces individually are going to get oxidized, right? And there's several different ways you can do this. There's one major subcategory of this that we're going to focus on, and that is called ozonolysis. Hey, think fast. What do you think the oxidizing agent we're going to use here is? Fantastic. Yeah, it's going to be ozone, right? ozone with a little help, right? There's two major groups of molecules that this can be done with. First one's alkenes. All right. So let's say we have an alkene. All right, whenever you do ozonolysis of an alkene, the first step is to add ozone, O3. And then the second step, it's a two-step process, is to add zinc and water. And again, mechanism of this, not going to go over it. It's in the book if you want to look at it. But one thing that's kind of nice about these cleavage reactions is the fact they are highly, highly predictable. They follow a very simple pattern that we can very easily use to just look at the setup, look at the reagents, and be able to figure out what we're going to get. All right. We said we're going to cleave, right? All right. Well, where do we cleave it at? Do we cut off the end carbon? Do we cut it in the middle? What? You're always going to target that double bond. You're going to cleave it right between the carbons of the double bond. So in this case, you got a 4-carbon alkene, double bond in the middle. You're going to cleave it into two 2-carbon fragments. I'm just drawing the carbon fragments. So those aren't the products. Those are just backbones. All right. Now, we said each one of those fragments are going to get oxidized, right? The oxidized carbon is going to be the carbon that used to be in the double bond, right? And so when they get oxidized to contain carbonyl. So basically the carbons go from CC double bonds to CO double bonds. And this happens to both of them. All right. Each one of these carbons already had an H attached to it. The H is still there. What type of molecules do we have here? What? Aldehydes. Yeah. Right. There's a pattern. There's a little guideline. If you have alkenes, that little O in brackets basically just stands for oxidized, or ozonolysis in this case. You always get aldehydes and or ketones. Sometimes you get ketones. We'll do an example of that in just a second. Yeah, ozonolysis of alkenes always gives you ketones or aldehydes or both. Okay. Go ahead, Race. Let me show you an example where you might get a ketone. Add an isopropyl group in there just to make things festive. There. Let's say we have that. Okay. Well, again, literally, here's your process. Find the double bond. There it is. You know that's where you're going to cleave. And if it helps you keep track of things, count your carbons. You know, make sure to keep the number of carbons correct. So you have 1, 2, 3, 4 carbons in one fragment. 1, 2, 3, 4, 5, 6, 7 carbons in another fragment. Okay. So that's sort of our skeleton in each case for each one of the fragments. All right. So let's try to find our oxidation. All right. So let's look at the bottom fragment first, the 7-carbon fragment. What's that one going to turn into? An aldehyde. All right. So which carbon's going to get the carbonyl group? Very first one. Yeah. So we get an aldehyde. What about the top one?
It's going to be on the second carbon.
Second carbon? Okay. So what do we have there? That's ketone.
Methyl ketone.
Yeah, specifically a methyl ketone in this case. That's not always going to be a methyl ketone. Well, sometimes it does. Right? And that's it. Isn't that nice? Don't you wish all OChem was this easy? Yeah, this is an exception to the rule. But it's nice to get those little tidbits, yeah, like throwing your dog a bone every once in a while. That's the way I kind of feel about this. All right. Are there any questions about that? All right. There's a couple of other situations that you might see. All right. The next one's going to be with alkynes. All right, so now we're going to be cleaving a triple bond. All right, I'm going to show you a specific reaction in a second. But basically, when you do this process, again, just like last time, you're going to get very predictable products, but they're going to be different. In this case, you're going to be carboxylic acid. And actually, now that I think about it, I should clarify this. This is going to be for internal alkynes. All right, let's just say we had that. All right, these are set up very similarly to the alkenes, with one difference. Alkynes are more reactive than alkenes. So with alkynes, you don't need the help of zinc. So those just require water. You don't have to have zinc. Alkenes you do. All right. So process is basically pretty similar to what we saw before. We locate our triple bond and we cleave it. And each one of the carbons, in this case, of the triple bond, now becomes a carboxylic acid. Right? Refresh me, what does a carboxylic acid look like? C double bond OH. Yeah. So, in this particular case, you would get that carboxylic acid. Then you'd also get a 2-carbon acid. There you go. If it was symmetrical, then you would get 2 identical molecules. Okay? Does that make sense? Questions? All right. Terminal alkynes. Let's look at that. Okay. Terminal alkynes are pretty similar, but with one difference. Okay. If you have a terminal alkyne, you know the carbon-carbon triple bond is going to be at the very end. So you know the size of one of our fragments is always going to be how many carbons? If you have a terminal alkyne, You cleave it. Yeah, you're always going to have one little end carbon that's kind of snipped off. All right? That's going to change the nature of our products a little bit. All right? You're always going to get a carboxylic acid and or carbon dioxide, CO2. If you make a one carbon fragment through oxidative cleavage of an alkyne, it's going to be CO2. So if we did this, for example, 5 carbon alkyne, we're going to have a 4 carbon fragment and a 1 carbon fragment. The 4 carbon fragment turns into the acid, just like we saw before. But since we have that 1 carbon acid, or excuse me, that 1 carbon fragment is going to be turned into carbon dioxide. In case you're wondering the Lewis structure of carbon dioxide, it looks like that. So it's sort of like a cousin of a carboxylic acid. What would that alkyne give you? What's that? 2 equivalents of CO2. Yeah. Once you cleave it, 2 1 carbon fragments. Each one of those gets converted into carbon dioxide. All right. So far, so good. Any questions? Hey, guess what? There's only one set of reactions left to go over in this chapter. Wow, we are rolling right along. This is also going to be one of the most important sets of reactions that we're about to go over for synthesis. You're going to be using these reactions in synthetic processes quite a bit, probably over the course of the rest of the semester. So definitely want to make sure to master these. All right. This is going to be oxidation alcohols. There's a lot of things we can do with alcohols. Alcohols are pretty reactive species. In fact, you guys got a taste of that in chapter 9. You saw like alcohols had a ton of reactions. They can also be oxidized, and we can put that to very, very good use. Right? And you think about it. An alcohol, has a carbon to oxygen single bond. Right? And this is the key right here. I'll just put an R. If we oxidize that carbon, what other types of species do you think we could make out of it? Think about it. As you oxidize an atom, you increase CZ bonds and or decrease CH bonds, right? How many bonds do we have in this case to an electronegative atom? Just 1, right? What do you think we could make if we had 2? Sort of like that, right? We can make aldehydes. We can make ketones. We can even oxidize alcohols multiple levels. It's possible in certain cases to go directly from 1 bond to oxygen to 3 bonds to oxygen. So we can also make carboxylic acids. So they're pretty versatile. One thing that's nice is certain alcohols will do certain things with certain oxidizers. So we can, it's not entirely a Wild West free-for-all of oxidation here. We can kind of keep things straight. I'm testing another marker. 1 second. Oh, that's much better. All right. Let's take a look. Well, think back to the alcohols chapter. First of all, what kind of alcohols could we have? You know, there's different types of alcohols. What are some of the different types of alcohols? Remember, some of them went E1, some of them underwent E2, depending on their substitution pattern. Ah, bingo, yes. Primary, secondary, and tertiary. All right, first let's look at primary alcohols. All right, there's a couple of different types of oxidizers that you can use, classified by either being strong oxidizers or weak oxidizers. The name says it all there. Strong oxidizers, they'll go much further than a weak one will, right? So, you add a strong oxidizing agent to an alcohol, it will go immediately from having 1 bond to electronegative atom to having 3. So this will make carboxylic acids. All right. So, for example, you have that primary alcohol. A strong oxidizer, if you look in your book, there's several examples. Several of the ones I named the other day. Potassium permanganate is a strong oxidizer. Dichromate ion is a strong oxidizer. I'll just use that one as an example here. Used in conjunction with sulfuric acid and water. Certain osmium compounds can be strong oxidizers. Be sure to look in your book. They'll have a list of common reagents that are used for this purpose, strong oxidizers, that you can select from. All right. And that'll convert this carbon directly from having 1 oxygen bonded, or 1 bond to oxygen having 3. Yeah. Well, let's say you don't want an acid. You don't want a carboxylic acid. You want an aldehyde or ketone. What type of adjustment do you think you'll have to make? What's that? You need to weaken that oxidizer somehow, right? You need something that'll oxidize it, but not so much, right? And there's basically one go-to oxidizer for this, right? If you take primary alcohol, do a weak oxidation, you can get aldehydes. Actually, you get aldehydes, that's it. All right, so let's take a look. We'll use that same alcohol. All right. The go-to weak oxidizer for alcohols is called pyridinium chlorochromate. We call it PCC for short. It's not PCP. I have had people put that on exams before. PCP is something else entirely. But PCC. And what that'll do is there'll be a gentle oxidation that takes this from 1 CO bond to 2. Okay? So basically, in a nutshell, there's 2 things you can do with primary alcohols. You can either turn them into acids or turn them into aldehydes, depending on what type of oxidizer you put in. Okay? Any questions on that? Sound good? All right, what about secondary alcohols? Hey, guess what? They're simple. They only do one thing, no matter what type of oxidizer you put in. Doesn't matter whether it's PCC or dichromate or potassium permanganate or whatever, it always gives you the same thing. Secondary alcohols always give you ketones. Okay, so if you take something like this, it's just simply going to replace that carbon-oxygen single bond with the carbonyl. However, you could add PCC instead, and guess what? It's going to give you the exact same thing. So those are a little bit simpler. You may wonder, well, why can't we do why can't we do more? Right? Why can't we turn this one into, I don't know, maybe like an ester or something, right? All right, one interesting thing that we can see here is, I've already got this, I'm going to erase it. I want to compare a couple of different alcohols. This is a primary. And this is a secondary. All right. All right. I'm also going to highlight the H's here. The H's on the carbon, the OH is attached to. All right. I'm not going to go over the mechanism of this, but I can tell you that a certain part of the mechanism involves this. It involves removing H's that are on the alpha carbon, right? Basically the same carbon that contains OH. For every hydrogen that's on that carbon, you can do one level of oxidation. Secondaries, how many do you have? Just one, right? So that means the maximum you can do is one level of oxidation. However, with primary alcohols, you got two. So that means you have the capability of going up to 2 if you have a strong enough agent. Does that make sense? Here's a question. We've done primary, we've done secondary. How about tertiary? Let's say we did this. A strong oxidizer in there. All right, what do you think is going to happen here?
Nothing.
Nothing? Wow, you sounded confident, sir.
You said it relied on the hydrogen coming off the carbon.
Don't have any here? You are absolutely correct. You cannot oxidize tertiary alcohols. They are unoxidizable. That sounds really kind of awkward, but I guess that's right. Yeah, it doesn't matter whether you put a strong oxidizer, weak oxidizer, whatever. You're just not going to be able to oxidize them because this carbon doesn't have any H's. So the mechanism can never get underway. Okay? Does that make sense? Are there any questions about oxidations of alcohols? Fun real world application here is that, and this is probably a little bit obsolete, but it has been used in recent years. you can actually use these reactions, or one particular set of them, to test blood alcohol level or give an approximation. Right? You guys have all heard of breathalyzers, right? Almost like I just want to ask, does anybody have experience with a breathalyzer? I won't ask that though. I actually have one in my office when I taught forensic chemistry. It's pretty fun to play with. You know, you can swish with mouthwash and blow into it, and it'll register that you have blood alcohol. I don't sit there drinking and then like, there's numbers. Anywho, those are the digital types, right? In the past, I know they have made more kind of sort of a cheaper, cruder home version of these. I don't know if they still sell these a lot, because now if you go to Walgreens, you can actually get some digital breathalyzers that are pretty affordable that you can have if like you have an alcoholic in the family or something, or you have your teenage kid and you're wanting to make sure they're not drinking beer or something. But they used to have these more, not digital, but much more chemically reaction colored based tests. They would have basically these tubes, and it'd have a little balloon at the end, right? And it would be filled with a packing material. And this packing material would be potassium dichromate. All right. And this has a color. You guys have probably worked with this in the past. I don't know if does anybody remember what this looks like color-wise, potassium dichromate? It's sort of a deep orange, sort of an orange red color. And that's because chromium is in the +6 oxidation state in that molecule. Chromium, when it's +6, looks sort of orangish red. All right, so the idea is that there would be like little markings, and this thing would be calibrated to correspond to a certain blood alcohol level. All right, you would blow into the end of it, right? It would have a balloon at the end so you could blow plenty of air in. And the idea is, if you've been drinking, well, what's the active ingredient in alcoholic beverages? You guys know? What type of alcohol? What's that? It's ethanol. Ethanol is a primary alcohol. It looks like this. Well, we have a primary alcohol. We have potassium dichromate. What did we just say happens when you have primary alcohol and potassium dichromate? What organic product does it give you? Yeah, look it up if you need to. Gives you carboxylic acid, so it gives you this, right? So this was oxidized, but remember, anytime something is oxidized, something's got to be reduced as well. In this case, the chromium gets reduced into Cr +3. And Cr in the +3 state has a green color. So basically what you do is you blow into this, and depending on how much blood alcohol level you have, that would determine how much ethanol got blown into here, and the red packing material would turn green. And so it gave you sort of a rough estimate of what the blood alcohol level is. Definitely not as accurate as the digital breathalyzers, but a pretty good tool to have, that's fairly affordable if you're at home. Like I said, these are sort of obsolete because the digital ones are pretty cheap now, but you might still be able to go into like a drugstore or something and find these. So. Kind of neat. Or I suppose if somebody was hypothetically at a party or something and they wanted to get a quick approximation of their blood alcohol level. I don't know why I wanted to do that, but shouldn't be driving and drinking anyway. But you see, so it's a pretty interesting little chemical application.
It only costs like $1 now.
What's that?
It only costs like $1 now. Good deal.
They only cost. How do you know how much it costs?
25.
What's that?
I'm 25.
Have you bought these?
Yeah.
Okay. I didn't buy any last week, so I didn't know.
Got bored.
Got bored. Just sit around, you know. Have a bottle of Jack Daniels in one hand and brush lights in the other. Yeah. See how many sips it takes you to get to a certain. That would be really cool. Cool. I've never actually met anybody who had experience with these before, so that's kind of neat. Someday I need to try to find some and bring them in for a demo. I could get some mouthwash, swish it, and then do it. All right. That's it as far as the reactions of this chapter. Any questions on what we've done in the chapter so far? We're not quite done with the chapter, but we're done with the reactions. Okay. Well, just like with anything else, now we can incorporate these into synthetic problems. So let's look at some synthesis here. Let me pull up my digital book. Let me find some good examples that we can work. All right. Here's a pretty good one. Okay. So basically, you're trying to convert that alkene into that carboxylic acid, and you can use anything that you want to here. Again, just like with several, just like we see quite a lot, there's more than one way you can go about doing this. I would say the minimum number of steps for this one would be 3. All right, let's work this one together. All right, so again, I personally think it's easier in most cases to kind of start going backwards. So I'm going to try to figure this out like that. I am going to take stock of what I have. I have an alkene. I'm trying to turn it into an acid. Am I adding carbons at any point here? No. 4 carbons in the reagents, 4 carbons in the product. So I don't have to worry about that. All right, so what I would do is I would look at this and I would ask myself, I need to make an acid. What is one way I know to directly make a carboxylic acid?
Yeah.
From what type of alcohol? Primary, yeah. We just learned that one. That's a pretty good place to start. All right, how would you make it an acid from a primary alcohol? What reagents would you need? Strong oxidizer, right? Potassium dichromate would work very well. Okay, very good. So now you need to figure out how you can go about making this alcohol. And that's going to include something that's not in this chapter. So it's kind of old. It's not last semester. We've done it this semester, but just not in this chapter. Let's see if you guys can come up with something. Any ideas?
Water in the presence of
Water in the presence of
an
an acid added to what?
to the alkene to get to the alcohol.
So this. All right, that's a good guess. That's a hydration of an alkene, right? However, if we look at it, remember, hydration follows Markovnikov's rule, right? So if you're looking at these two guys, this one's going to get the H, this one is going to get the OH.
We're going with the BH3 and magic.
The BH3 and magic, yeah. Yeah, you want something that's anti-Markovnikov, right? We learned that if you do a hydroboration oxidation, that would result in an anti-Markovnikov addition of water. And that is a two-step process, so that does count for 2 steps. BH3, H2O2, OH minus. That'll put the OH on the end carbon, and that can then be oxidized into the alcohol. Okay. Does that make sense? How we got that? Any questions about how we did that? Another one. Ah, crud, I lost my place. Give me a second, let me think here. All right, now we're getting to some good stuff. This one's a little bit more involved. Let me see. Let me think and see if I can figure out in my head how many steps. 1, 2, 3. I think 5 steps is this one. Yeah, I know, right? Jesus. Well, let's do it one step at a time. All right, let's take stock of what we have. Terminal alkyne. And we have a diol. We have a vicinal diol. All right, with stereochemistry indicated. Are we adding any carbons?
1.
1. So we do need to add a carbon along the way somewhere. Okay. What do you notice about these 2 OH groups? Same side, right? So you can basically say that this is a syn diol. Do you know any ways to make species that has 2 OHs on the same stereochemical side? Dihydroxylation of what? Using KMNO4 on what? An alkene, yeah. Actually, I may have this wrong. This may be 4 steps. I may have miscounted. I'm not sure. Yeah, this is a syn dihydroxylation that you can do. If you have that particular alkene, right? We learned that one the other day. Very reliably puts OHs on the same side. So actually, yeah, I think this is 4 steps total, not 5. I'm miscounting. All right, so now you need to figure out how to go from there to there. My next step in thinking here, and again, you can sort of find your own methods. I might at this point try to figure out a way to get that extra carbon on. All right, what's one way that we learn to get extra carbons onto a chain? A satellite ion, right? If you take this is a terminal alkyne. You can certainly make an acetylide out of it. All right, what would you react it with to get the extra carbon? What's that? Okay, and what would be attached to the methyl group? Halide, right? An alkyl halide, a 1-carbon alkyl halide. And boom, you've got the right number of carbons. Now you just need to link these together somehow. How do you get from here to here? How do you get from an alkyne to an alkene?
Can you use the H2 again?
Can't use that. That's a strong base. So that would be looking to pluck a proton. We learned a couple of different ways to make alkenes out of alkynes. And this was actually in this chapter, I believe. It was early in this chapter. Quick note, I just happened to draw the trans alkene here. Either the trans or the cis would work fine here, but let's just go along the lines of what I've drawn. How could you make a trans alkene out of an alkyne? What's that?
Hydrogenation.
Catalytic hydrogenation. That would actually make the cis alkene. Which, if I had drawn cis there, that would work fine. You could go through the cis and it would work. But since I have trans drawn there, let's just go ahead and put that particular reaction in.
Would be the 2Na and 2NH3.
2Na and 2NH3s. Again, I want to reemphasize, this particular pathway doesn't rely on this being trans. You could have done the cis pathway as well, but I just happen to do the trans. So that's it. That is a 4-step synthesis. As you see, they're starting to get a little bit more complex. Right? Or were you able to follow the process, though? How we got that? All right. Well, next on Friday, we'll do another synthesis or two for practice before we get into the next chapter. All right. That's all I got for today. So if you guys don't have any questions, I'm done. And you guys can start worrying about your genetics exam. Good luck. Marissa, you okay? I saw you rubbing like you're having heart palpitations or something.
I had like a sharp pain right here and here at the
Oh,
same
gosh.
time.
Stress.
I probably am stressed.